Okay, so good evening. Am I audible?
Yes, sir.
Hold on a second. Let me. Hello. Yeah. Am I audible?
Yes, sir.
Okay. Fine. Okay. So, uh, good evening, everyone. Welcome to the final session of this NPTEL Real-Time Signal Processing course, PMRF sponsored. So, okay, so today is the last session of this course, and this will run for only an hour, unlike the previous sessions. And we will revise. I won't be solving problems anymore, discussing new concepts anymore, because all of them have been covered in the earlier 12 lectures. And if you want, you can access the link that has been provided by NPTEL to see the previous sessions, and as well as the corresponding PDF notes have also been uploaded. I am yet to upload this week 12 note, rest of them have been uploaded. So I will just briefly review all that we have learned so far in this journey. Okay, so let's get started. Let me just review what the revision had started the last week. Okay, so initially the course started with number system as well as the DSP architectures and a bit of multipliers. So in week 12 we talked about number system, where we first talked about unsigned numbers. And basically unsigned numbers are used in image processing in images, where the pixels are generally 8-bit unsigned numbers. When you say 8-bit or any r-bit number, so it ranges from 0 to 2 to the power r minus 1. And hence for an 8-bit you have values from 0 to 255, which I had showed you earlier in the previous image processing portion, where these sliders range from 0 to 255 for colors. Okay, so coming back, so when you have an unsigned number, the lowest values have all zeros and the highest values have all ones. And we then talked about that when we add two n-bit numbers, the resultant number has to be represented in n plus 1 bit numbers, otherwise you have something called overflow. Similarly for signed numbers, or the especially we use the 2's complement representation, because you don't need any extra logic for determining whether the number is positive, negative, greater than, lesser than. Okay, which would have to be done if you had to use sign bit representation or the 1's complement representation. Okay, so if for an r bit number, it ranges from minus 2 to the power r plus minus 1 to the power r minus 1 minus 1. And for negative numbers you have the most significant bit 1, and for the positive numbers you have the most significant bit as 0. So for example, an 8-bit number ranges from minus 120 to 127. n-bit signed numbers, as earlier, if you need to represent them their summation using n plus 1 bits at least. And if you want to fix them as n-bit output, then you may encounter a scenario called overflow. And what happens during overflow? In overflow, the sum of two positive numbers becomes a negative number. You see that it doesn't become it, you see that it comes out as a negative number. Or the sum of two negative numbers yields a positive number. That's what you see, that the MSBs are 0 and the some MSB is 1, and vice versa. Similarly, in the number line, if you try to see the representations, a negative most number will have maximum number of zeros and only one MSB 1. And as you decrease the magnitude of the negative number, you will have more and more ones. On the other hand, if you have, okay, so it rotated in my, so if you have a positive number which is very low in magnitude, so you're going to have lots of zeros. And if you have a positive number with high magnitude, you are going to have lots of ones. And then I showed an example of overflow. And in order to prevent overflow, you need to do something called sign bit extension, where you copy the sign bit of the MSB once again to the left side for the adder and addender. Okay, and then you take the first 5 bits of the summation and ignore whatever carry comes after that. Then we talked about the fixed point number representation, where you dedicate the first m bits in the MSB for integer as well as sign representation, and the last n bits for the fraction representation that I've shown over here. This is the decimal point. Actually there is no decimal point in that hardware. It is something that is implied. We engineers have to keep this in mind as a reference. So all to the left, you have the integer part, so this is your MSB bit as usual, and over here you have the fractional bits. So for NQMN bit number, the ranges from -2 to the power m minus 1 to the power m minus 1 minus, okay, the resolution is 2 to the power n minus 1, so it will range up to 2 to the power m minus 1 minus 2 to the power of minus n. Okay, and then I told you how to find the value of q1.3 or any arbitrary decimal number in fixed point representation from binary to decimal. Okay, and then there were lots of theoretical stuff regarding computer architecture, the control. There are 3 portions of a microprocessor. You have the arithmetic logic unit, then the control unit, and input output devices, how they're connected, and our main focus is on the arithmetic and logic unit. So there are various kinds of instructions that can be processed by an processor: direct mode, indirect mode, addressing modes. So you have to revise them. So the special ones for the DSP is the bit reverse addressing mode, in which especially finds use in the FFT. So what happens if your inputs are in line? So if your inputs are in line, like 0, 1, 2, 3, all of them in order, then if you do decimation in frequency, which you shall be seeing very soon if time permits, so you have to reverse the order of the bits. So 0, 0, 1 becomes 1, 0, 0, and so on. So you see, when you have 0, 1, 2, 3, 4, all of them parallel in line, then the outputs come in a different manner. Okay, this is called decimation in frequency manner. And if you do the opposite, do the other way around, if you want to keep the frequency components in order, then you have to do the same ordering, x of 0, x of 4 for the time domain input, and what you get is decimation in time domain and decimation in time FFT. And circular addressing mode is finds use in the FIR filters, where you have, say, in the equation h0 xn plus h1 xn minus 1 and so on. So as samples keep on coming, as n keeps on moving, so you need to repeat the multiplication with the same indices after the filter length. So that's how we talk about the modulo structure. Then we talked about feed forward pipelining, where we initially talked about 4 types of critical path. This is especially important when you might be given questions to solve regarding finding the critical path of a given circuit. You may be given a signal flow graph or a block diagram where there will be a bunch of adders and multipliers, and you need to check the critical path. So what are the types of critical path possible? It's input to out. It can be input, and note that a critical path should never have the delay element or a Z inverse element, which is a register or a flip-flop. So input to output, and this path between input to output should not have any register. It can be from an input to a register, it can be from a register to an output, it can also be from a register to a register. Okay, so we took this example of a 3-tap FIR filter, where we found that the critical paths are shown over here, as you can see, and the corresponding delay is Tm plus 2Ta. So Tm plus 2Ta, as you can see over here, the path, there are 2 paths, but the delay is the same. You have a circuit can have only one critical path delay. So this is for a 3-tap filter. So you can understand that if I increase the order of the filter, then the critical path will increase linearly in the order of n, so it becomes Tm plus n minus 1 Ta. So that actually limits the maximum clock frequency with which we can operate fine. So this I have shown over here, the maximum clock frequency with which you can operate this. So we use, in order to tackle this, we do something called feed forward pipelining. So what happens when you have some certain graph like this, okay, certain circuits, so you try to you try to find a line that cuts this graph apart, and you get two disjoint graphs. Okay, so when you get two disjoint graphs, and all the lines when you cut, they should be in the same direction. You cannot have something like one line moving in same, one line moving in opposite direction. You can't draw a cut set through this kind of a line. All the lines should be in the same direction like these. Okay, this is allowed. So as you can see over here, all the lines are moving in same direction. So you draw a line and cut that, and you put registers in it. You have to check appropriately, because you can't put arbitrary number of registers, otherwise that would increase the power consumption of your circuit. So you should show two examples. I'm not repeating them, please check with the earlier video lectures, I mean the PMRF session lectures especially. So I've covered both in week 2 as well as in the week 12 how do you find the critical path of any circuit. So we found out that by critical path feed forward pipelining, we can reduce the critical path delay. And then another method was the transposition theorem, where you follow these rules and you get to change the structure of the filter. What happens is that if you do transposition, the equation or the functionality does not change, but then you see over here, rather than in the earlier case we had the entire arrows in a same line, all of them in series, but in this case you can see the arrows are intervened by the delay registers. Okay, so that is especially reduces our critical path delay. Okay, so that's what I covered in week 12, and it was what was covered in week 2. Let me check once again. Yeah, so week 2, in week 2 we had a good deal of discussion regarding all of these, how to find critical path, maximum frequency. So we see, if you if you see the week 2 lectures in detail once again, you can refer to those lectures and revise. And you can also look at Keshav K. Pari's book if you want to practice some problems. Similarly, I had told over here non-linear, linear systems. I talked about, okay, so here I talked about let me go back. So here FIR filters, okay, fine. We had talked about somebody asked a question about impulse response, and then what are these delays representing. So it's a register, so set of D flip-flops. So how this kind of thing works. So general FIR response looks like this kind of a summation, H0, H1, Z inverse and so on, representing delayed samples. Okay, and then we also have this Bauli multiplier and unsigned multiplier. You can look at that in the lecture slides for the diagram. Okay, so 8-bit cross 8-bit will all give me how much? 8 plus 8, 16-bit. I had discussed this question multiple times, how to have an m-bit and n-bit number when multiplied gives m plus n bits. So okay, analog, so basically this came from the fact that you can never design FIR filters using analog filter transforms. You can design IR filters from analog filters. Okay, like analog filters like Butterworth, Chebyshev 1, 2 elliptic filters. And then linear filters have a good advantage that you can design linear phase. So what is the condition for linear phase is that the filter coefficients can be even symmetric or odd symmetric, and then there are 4 types: type 1, type 2. Type 1, type 2 are the filters where you have even symmetry. Okay, xn equal to xn minus 1, the plus sign will be valid, whereas for type 3 and type 4 the negative sign will be valid. Okay, you see the anti-symmetry over here. So what happens in the if the system is the linear phase system? So basically your real actually in real life your signals will have multiple frequency components, and you would like to ensure that all the frequencies get delayed by the same time. Okay, but if you don't do that, then the different frequency components, as I can have shown over here, that if there's a pulse over here and it has a sync response, and if it's linear phase, then all the sync functions, the corresponding frequency components will have equal time delays. But then if you do not have the linear phase system, then the frequencies, different frequencies will undergo different shifts in time, and the resulting waveform will be scattered in time, and as a result of this you may encounter something called intersymbol interference, which you might have studied or will be studying in a digital communications course. Okay, so yeah, so once again repetition of how to find the critical path and the delay. Yeah, and you also mentioned that the number of taps is actually dependent on your frequency specifications, frequency response specifications, like pass band, stop band, pass band ripple, stop band ripple, so on. That was week 2 in a very fast gist. Then we come to week 3. Let's see what we had covered in week 3. Oh God, I think we had covered a lot of. I doubt I will be if I will be able to revise this completely. So okay, so basically we had talked about we are discussing problem solving methods. So there's an audio signal. Okay, so basically when you have a sampling system, okay, a sampler followed by an A to D converter. So basically an ADC actually contains a sampling circuit and as well as a quantizer. Okay, so before that you have to ensure that you sample the Nyquist rate. In real life your signals are not band limited, they have infinite bandwidth in reality. However small the energy is, you can never have zero energy at some very high frequency. That will be minuscule, maybe minus 800 dB, but then it's not zero. Okay, 800 dB doesn't matter, but still at surf, but you may have some issues. Your system even at certain requirements as well, you may have a system which has a bandwidth of 40 kilohertz and your signal ranges up to 30 kilohertz. Okay, so for 40 kilohertz sampling rate you must have a bandwidth of 20 kilohertz signal. So in order to ensure that you do not undergo aliasing, you do something called AAF, which is the anti-aliasing filter, which is a low pass filter. Okay, so when you do anti-aliasing filter, you ensure that there is no overlap, and for that what happens, you choose the cutoff frequency as that is less than or equal to the half the Nyquist rate. Okay, and if it's greater than half the Nyquist rate, then you have something called aliasing. Okay, and here somebody was asking about addition of numbers in Q13 system. So I think you can convert to and fro numbers in using the method that I discussed in week 2, and then you can do normal binary addition. And in these, especially in the exam, you should not directly add up the numbers. You should actually do the binary addition itself, because sometimes they may intentionally give you a question where there is an overflow. Okay, and you have to give the answer in the overflow form. I mean, the wrong answer actually has to be given. The wrong answer is the correct answer. But if you add the numbers directly, you will not do the overflow, and you will give that answer and you will end up losing marks. Okay, so I had told I was talking about how to convert an arbitrary decimal number to binary number. You keep on multiplying by 2, check the number post into the left decimal. If it's 0, keep 0. If it's 1, keep 1, and then remove this 1 and then multiply again this decimal part by 2. Okay, fine. And then the frequency response. Okay, so we also talked about how to obtain frequency response from pole zero plots. So in digital filters, the frequency ranges from 0 to 2 pi. But actually, what happens when you're dealing with real signals, not complex signals, real signals, real systems? So we have this mm, conjugate symmetry, x of omega equal to x star of minus omega. Okay, so because of this scenario of real signals, the whatever you see in the upper half, okay, the magnitude response will be the same in the lower half from pi to 2 pi. So if you see evaluate the response from 0 to pi, the magnitude response, let's say from 0 to 5 is something like this. The magnitude response will be the same, it will be the mirror image, okay, and then the phase response will be the anti-symmetry. Okay, like this one is the symmetric, but this one is the anti-symmetric phase because is x star of minus omega. So I told how to evaluate the frequency response. Suppose you have a pole, okay, so what happens wherever you have a pole, you assume let's say pole is over here. So when you have to start from this point on the circle and move around the circle, and depending on whether a pole is close to you or zero is close to you, accordingly you have to draw peaks or dips in your frequency response. So you need to actually plot from 0 to pi only. Start from some value, unless you have a 0 at the zero frequency, you should start from some intermediate value and then move around like this and see, and then I will telling you continue how to do. Okay, so so let's suppose there's a pole at angle pi by 6. So if you're standing over here, let's you say you keep as it is. As you move closer and closer, you are approaching the pole, and a pole blows up. Okay, the pole is like a real street lamppost pole. Okay, so you can climb up a pole, you can never climb down a pole. Okay, so as you're moving upwards, the pole, you're moving closer to the pole, you are actually climbing up indirectly. So as you move closer and closer and you move ekdam perpendicular to the pole, you have the peak. Okay, and once as you move past this pole, it starts dipping. Okay, so whenever you have a pole, okay, so as you move towards the frequency of the pole, you will get to see dip peaks. Similarly over here at 3 pi by 4, as you move over here, see, as I move close to 3 pi by 4, there will be a peak and then a dip. And one more thing, the closer your pole is to the unity circle, the higher will be your peak. You see at red, the red is not allowed because the red is directly on the unit circle, and if a pole lies on unit circle, then it's an unstable system. Okay, but as you move away from the unit circle, the amplitude or the peak with height will reduce. Okay, similarly if you have zeros will behave opposite to the pole. So 0 will pull you down. Okay, so just as 0 marks is not allowed, 0 pulls your life down, so a 0 will actually pull you down to 0 or try to pull you down to 0. So if a 0 exactly lies on the unit circle, so it pulls you down to 0. But if a 0 is not on the unit circle, depending on how close it is, that will determine the magnitude of a dip. So over here, let me be over here, and as I move over here, I am getting closer to the 0 over here. So I am slowly dipping. As I reach ekdam perpendicular to this 0 at pi by 6, I reach the minima, and then as I move away from the pole, sorry 0, I again rise up because I am away from the 0. And again, once again, if you see, as I move closer to the unit circle, the magnitude of my dip will become higher and higher. Okay, more and more. If it's directly on the unit circle, then I will touch 0. Okay, and then we solved an assignment question in which this kind of a structure was given. Okay, and based on this structure, we had to find whether it was a high pass, low pass, what was the expected one. So we then took this, we then first wrote this in time domain, convert this into frequency domain, find the frequency transfer function in terms of z. Okay, once you have the transfer function, try to find the poles and zeros. So what do you obtain? There's a pole at 0. Pole at 0 won't harm you because it's the farthest away from the unit circle, and the zeros are at -1 and +1. When you have a 0 at -1 and +1, that means you are going to have the dip at pi omega equal to 0 and omega equal to pi. So omega equal to 0, omega equal to pi will have the lowest frequency response amplitude, and then if you are moving away, so you will have a peak. So it's like a band pass filter. Similarly, we had mentioned over here that if you want to make your filter even sharper, then what you can do is adjacent to the pole you can put multiple zeros to its left and right side. Okay, so that will try to compress your, that will try to squeeze your frequency peaks into that region and dip the amplitude in the areas outside it. Similarly, for notch also we can do the same. Okay, so again somebody had asked a question on how to find the critical path. So as you can see, if you have studied or practiced questions properly, I'm sure you'll be able to do these questions. Yeah, so these are revision questions on okay, so this is actually the a filter structure of a linear phase filter. So basically you are actually sharing the multipliers between the samples. So over here there was some concept of C charge parallel processing and pipelining. I don't think I will be able to explain that. Okay, so whenever in case if you're when you'll be solving the time equations for parallel processing and pipelining, if you might have to calculate the charging capacitance. So when you have to calculate the charging capacitance, you will have some particular critical path, and you need to directly add the capacitances of the elements in the critical path. For example, in this circuit, the critical part is this, so the corresponding charging capacitance will be Cm plus Ca. So I have repeated transposition multiple times. Okay, and this is the basic structure of an IIR filter, where you have these delay loops, okay, feedback loops over here, and then I told about two primary implementations for an IIR filter. The direct form one, where you have the FIR portion followed by the IIR portion. Okay, we implement the zeros first and then the poles, and then if you look at the number of delay registers, that's m plus n. Okay, and then you have the direct form 2. What do we have? We actually implement the poles first, the feedback loops first, and then the zeros. Okay, as of now, does anybody have any doubt or finding any issue? Okay, I guess no. So there are and then what you do in this case, you actually end up sharing the storage elements, the delay registers, and because you're sharing, your number of delay registers ends up being maximum of m comma n. And what is m and n? M and n are the order of the polynomials in the IIR filter, numerator and denominator. Okay, and then I talked about some second order section. Okay, important second order sections are something that are used in the implementation of cascade of IIR filters more efficiently, because we talked about there in our week 3 or 4 that we have these quantization issues and there might be quantization noise coming up, and we want to ensure that our structure is such that it does not end up amplifying its own quantization noise. So we actually what we do is that we implement the filters as cascade of second order systems, and second order system looks something like this. And now when we have to make second order systems, what we do is that we have to correspondingly we need to pair poles and zeros. So what happens is that we first pair the pole and zero closest to the unit circle, and then the next most closest, and then the least closest. Okay, so all of this is also mentioned in the book of SK Mitra in digital signal processing that I referred long back. That was week 3, I guess. There, here we have week 4. Okay, so yeah, so we are solving a question of how we implement multiple poles. So this is a unit delay system. Okay, so actually I should have given a d over here, and all of these are missing. So correction, all of them should have a delay element because Z inverse has to be implemented. And then I was explaining the general arbitrary if you have arbitrary pole positions at r1 e j theta, r2 j e theta, and then if how do we find the corresponding IR filter, how can we get the fourth order section. And then if you have studied signals and systems, this will be very easy to understand, is very easy for you. The left side of the S plane is a stable plane. You have the real part negative, and the imaginary portion denotes the frequency of oscillation. This is the damping factor or the exponential amplification factor. So your S plane e to the power st sc sigma plus j omega. So e to the power sigma t is your envelope. If you're on left half of the S plane, then you have decaying envelope, and your system or the system impulse response is stable because you are going down and down. Actually the h of integral over h of t is, sorry, what am I writing, integral over mod h of t dt is less than infinity. So it's in fact it is BIBO stable, or you say stability in some other sense. In other hand, if you look at this rising for an input impulse input, you have this such exponentially scaling outputs, which is unstable system. So right half we cannot afford to have poles, left half we have poles. That's good. Okay, so an important thing is that often in real life, in ideal systems, the filter coefficients that for a particular design have infinite precision. That means when you actually do it in a computer, you're actually using floating point system, and that has very high precision and very high range as well. But then in real life, when you are implementing signal processing systems on real devices on low power or other DSP systems, then they are implemented on using fixed point representation. So then it so happens that you need to quantize the coefficients, and when you quantize these coefficients, you often end up having different responses. So you're not looking at the response portion anymore. Now we are looking at problem solving. So how do you actually solve? So suppose you have initial some coefficients a and b, and they have written as a0 and b0. So what do you do if you want to quantize them to n bits? Okay, so once you quantize into n bits, you have some new coefficients a0 tilde and a1 tilde, and then now you need to factorize them and obtain the new coefficients. Okay, so for example, you have some coefficients, say 0.48, and what do you want to do? Let's say I want to quantize it to 3 bits. So I will try to convert 0.48 into a binary fractional number. So we'll use the same multiplication by 2 format to actually obtain this 0 1. So it's 0.01. Okay, and when you when you just keep it to 3 bits, 0.01, you actually end up getting a different coefficient, that's 0.25. So if your number of bits are quite low, then you may end up having a completely bad response. Let me yeah, and similarly, okay, So when you have n bits, so I'm assuming 1 bit for sine and n minus 1 bits for magnitude. So what do? Let's suppose you have a positive number f, it's a 0.573. You multiply that by 2 to the power n minus 1, okay, and then you take the, for there are two types of quantization, one is truncation and one is rounding. Okay, truncation actually entirely removes the unrequired LSBs. Okay, this is very easy to do in hardware, but the problem is that you have a bit more. Average error is actually not zero, average error is LSB by 2. But in case of rounding, what do is that you actually round it to the nearest number. So that is a bit more costly than truncation, much not too much, but bit costlier than a truncation. Truncation does not require any hardware at all, it is just hardware removal, but rounding requires some additional hardware. But then the frequency response or the performance is a bit better, which is comparatively better in fact for rounding. And in fact, if you want to achieve some performance, if whatever you can achieve using, let's say, 5 bits of rounding, that can be achieved using, let's say, 7 bits of truncation. Okay, so let's say 0.48 and 3 bits I want to truncate it to, so 0.48 into 2 to the power 3 minus 1. And now what I do, I find the floor function. So if it's 1.92, I take 1 and divide by 2 to the power n minus 1, 1 by 4, so see 0.25. And what do you find over here? 0.25. Fine. Yeah, quantization, truncation and round off. And in the case of round off, what we do is that we add plus 0.5. Okay, so what happens because of adding plus 0.5? If between, let's say, a and a plus 1, if the number is within this range and you don't add 0.5, it stays within this range. But if it's over here, it gets approximated to this number. Okay, so basically it actually is 0.5 actually helps the number to get shifted to yet another the closest number. So 2.42, and then we take the floor 2 by 2 to the power 2, that's 0.5. You see 0.5 is much closer to 0.48 than 0.25, so rounding will give you a better response. So for summary, what do? Truncation, quota coefficient multiplied by 2 to the power n minus 1, floor of that divided by 2 to the power n minus 1. Rounding, what do? Number or coefficient into 2 to the power n minus 1 plus 0.5, floor of that divided by 2 to the power n minus 1. Okay, so we are talking about L norm. So L norm also we saw in the assignment, you can obtain by simply square root of the Euclidean norm of all the coefficients, 1 plus 0.6 square plus 0.25 square. That's how that answer was obtained. But actually L2 norm was something else, but for exam purpose, if you get it, don't go for all these big calculations. Then we talked about time domain to signal to frequency domain conversion. So when you have continuous aperiodic and aperiodic signal time domain, in frequency domain also it's continuous and aperiodic. As you can see, Gaussian becomes Gaussian. When you have continuous and periodic in time domain, it becomes discrete and aperiodic. Okay, continuous leads to aperiodic and periodic leads to discrete. Okay, this is the important thing. So when you have such periodic signals in time, you get something called discrete time Fourier series. And when you have the other way around, discrete and aperiodic, discrete leads to periodicity, aperiodicity leads to continuous. So you have a discrete time signal which is aperiodic, you get periodic continuous time DTFT, discrete time Fourier transform. Similarly, when you have discrete and periodic, that will again lead to periodicity and discrete. So this is the discrete, requires the discrete Fourier transform. Okay, so what did I cover over here? Okay, so I covered how continuous time analog signals gets converted to discrete time analog, and then it becomes discrete time discrete amplitude. So sampling converts from analog to discrete time, and then quantization converts continuous amplitude to discrete amplitude. Okay, So you have certain bits per sample. Yeah, and then we started talking about DFT. So you have, let's say, 0 to n minus 1. Your input signal has n samples. Then what you can find, how you can find a DFT is this equation x. This is the analysis equation of the discrete Fourier transform. And then we talked about these are the basis functions, just like in the Fourier trigonometric Fourier series, your sine and cosine functions are the basis functions. Basis means these are the main signals upon which you put on your amplitudes. You try to construct your signal from sines and cosines. And in the case of discrete Fourier transform, these are your basis functions, and they are finite in number, 0 to n minus 1. This term e to the power minus j to n is called a total factor, represented by w of n. Okay, and then we talked about evaluating omega equal to 0 implies 0 frequency of DC. Omega equal to pi implies that you reach the half the Nyquist rate. Okay, so 0 to 2 pi, so 2 pi is fs, which is a Nyquist rate, and your signal has a bandwidth of Nyquist by 2. So the maximum frequency of a signal is represented over here, because you have not acquired anything more than the maximum. So here you can see 0, 2 pi, and you have a correspondence also, omega k equal to 2 pi k upon n. And you can, how you can map, so a frequency and the angular frequency in radians, 2 pi corresponds to fs. So correspondingly you can obtain the frequency for any of these points over here. So we had great details discussion. Okay, and then as I mentioned earlier as well, in the real life signals, these are complex conjugate. Okay, x star k x of n minus k, because of it, that's why when you plot the frequency response in MATLAB, you only plot the first half. And these are certain property, and this property will help you in solving multiple problems in the exam. If you are said that some samples, let's say of the DFT are given, let's say x of 0, x of 3, x of 5, x of 7, then the other samples can be simply found using this equation. Okay, and then if you're asked to find the x0, x1 and all those, you can use the inverse DFT equations. That was what we had covered in so that was week 4. And then in week 5 we revised DFT. Okay, and then twiddle factor. Okay, so same repetition. Okay, you can go through my notes. Twiddle factor has two important properties. One is the symmetry, wn of k plus n by 2 because minus wn of k, and then that's how, and in fact that one this symmetry property helps in simplifying the fast Fourier transform as well. This was the symmetry, and the periodicity is wn of k n plus n is wn of k. Okay, and then we talked about why and how circular convolution. So generally when you have an m point and an n point signal, you convolve them, you get an m plus n minus, linearly convolve them, then you get an m plus n minus 1 length sequence. But let's suppose you take xn, and let's say you take xn and then convert it, do its DFT, you obtain an m point sequence, and hn you do its m point sequence. Okay, but then you cannot multiply them because the number of the DFTs will have different sequence lengths, so you can't multiply two different sequence lengths. Okay, so similarly what do you need to do then? We actually need to ensure that both xn and hn are of same length. So what do? We append zeros. we append zeros and make them a common length L. And what was L? L was nothing but m plus n minus 1. We ensured that these signals become equal to the length of the final convolution. Now once you make them L point, you take xn, append zeros, take DFT, same thing you do with hn, you multiply the two DFT sequences, and then you take the inverse DFT, okay, and then you get yn. But then the yn that you get back from IDFT will not be the same as linear convolution, okay. What you get is something called the circular convolution. Okay, in case you have appended zeros, you will get the linear convolution, but for other cases, general cases, your circular convolution is not equal to the linear convolution. And then I showed how to do linear convolution. You must be knowing this because you done signals and systems. And then how to find the circular convolution. Let's say you have a 4-point, okay. For example, you consider a 4-point DFT. So keep the first 4 samples as it is from your linear convolution, and then the last 3 samples you take them and add them with the first 3 samples, okay. Like 1, 3, 5, 6 I keep them as it is, and the next 3 samples I place them just below the first 3 samples, and then I add them and I get the 4 samples, okay. So you see, it's like aliasing in time domain. So for example, you can see circular convolution and linear convolution are different for some 2 4-point DFTs. So this zero padding actually helps prevent them from happening. And then we also found that the computational complexity of this DFT is of the order of ON square multiplications and ON square additions, okay. So that's why we use the radix 2 FFT or some FFT, which actually reduces the computational complexity. It is not a transform. FFT is of 2 types, decimation in time and decimation in frequency. So decimation in time means that you take the samples and then break it into 2 halves and then compute DFT of the half. And when you compute a DFT of the half, you again break it into 2 halves and again compute the DFT of the 2 halves. You keep on doing recursively. So what actually ends up happening is that I'm not going anymore into this. See, x of k was divided into 2 f1 and f2, and then you use their DFTs, and f1 is further divided into v1 and v2, so on like that, okay. So and this is what I was saying. So 4-point DFT on each of these, and then you combine the results, and then this 4-point DFT is obtained by 2-point DFT and 2-point DFT, okay. And this is the unit butterfly structure. And then we have the computational complexity of n log n. So DFT is n square, radix to FFT is n log n. And the basic structure for decimation in time is this. We have a twiddle factor multiplication followed by a butterfly, okay. Keep this in mind. Twiddle factor multiplication followed by decimation, followed by butterfly. And this you can, if you go to the earlier lectures, you will be able to see how I have derived these things in detail, okay. Once if you remember how to derive this, then you can easily remember the structure. Similarly, we have something called the decimation frequency, where you divide the frequency response, the FFT response, the frequency domain samples into odd and even, and then evaluate them accordingly. So the corresponding equations are also a bit different, and you see the basic structure is actually butterfly followed by a twiddle factor multiplication. So it is the transpose of DIT. Okay, so important formula is that ADC has a signal to noise ratio for sinusoidal inputs as 6 times n dB, where n is the number of bits, okay. And then the noise power is delta square by 12, where delta is the resolution of your ADC, and delta resolution you can calculate by the full range -1 to +1 or voltage full scale range divided by 2 to the power n, or the number of bits. So you go through the lecture notes for the details. Okay, week 6 we had revised circular convolution, and then overlap and overlap save A50. So overlap and an overlap save A50 was done because we have long duration signal, so you cannot apply A50 on them directly. What you need to do, you need to break them into chunks and then apply A50 on them. See, you need to break them into 10 millisecond chunks, and then for each of them there's a long algorithm. You need to append zeros, then in the filter also you need to append zeros, and then evaluate the product. You need to keep on doing this for multiple such chunks, and then finally you need to add an overlap. See, there a previous chunk and the next chunk has an overlap between them, and this overlap has to be added. This is the overlap. And overlap save also, the first few steps are similar, but in certain cases you need to actually discard. Okay, I'm not repeating them anymore, that's too long, it will take and it's like repeating another lecture. Overlap and discard. And then we talked about correlation, which comes from statistics point of view. So like two random variables, if increasing one random variable also increases another random variable, then they are said to be positively correlated. If increasing one random variable decreases another random variable or vice versa, then they are said to be negatively correlated. If increasing one random variable does not lead to the change or any manipulation in the other random variable, then they are said to be uncorrelated. And then okay, for example, we showed over here positive correlation, negative correlation, zero correlation. For deterministic signals, okay, so this was the important formula. We gave an example of radar, how radar signals are detected using correlation filters. Okay, so important formula is xn into h star of minus n, because you're doing x of n into h of n, so correspondingly star if h of n minus 1. Remember this one. Okay, and we have to do a convolution, and then you need to, important thing is that you need to find the zero crossing. Now how do we find the zero crossing? Multiply xn into hn directly and add them up and see the point where the convolution is matching. Okay, and that is your 0 point. Correlation coefficient is a special coefficient for showing correlation, so it ranges from -1 to 1, and as I mentioned, -1 is 100% negative correlation, 1 is 100% positive correlation, 0 means no correlation. And then you have the autocorrelation coefficient, which is a special version of the normal correlation where you are matching a signal with itself. And the Fourier transform of the autocorrelation function, x of n times x star times x of minus n, is the power spectral density. And then this is also an important formula. You may have numericals from this. So if you have a random signal which has a power spectral density of sxx omega, and you pass it through a deterministic system, okay, the system is deterministic, h of n, which has a frequency response h of omega, then you get an output which is again random, but its power spectral density is yy of omega. For additive white Gaussian noise, we mentioned that it has a correlation which is a Dirac delta function. That means it's uncorrelated with its consecutive values, it's only correlated with itself. Well, lots of variation, power spectral density. So that was week 6. I know I'm going too fast, but then okay, then we talked about adaptive signal processing. That's in order to understand how we given a signal, how do we detect the signal in presence of noise, how do we change our filter if our signal changes, eliminate noise and extract sinusoid. So for example, I told band pass will not work if your filter changes. So adaptive signal tries to manipulate filter as that it changes with the change in input signal characteristic. So basic structure is that you have a single input signal, you have a filter whose coefficients are variable, and then you get a corresponding output. That output is subtracted from a desired signal, and the corresponding error is passed into the adaptive algorithm, which tries to use some learning rule, gradient descent or something, general gradient descent or something else, to manipulate the filter coefficients. And in it, what happens, you actually end up modeling the system which produces takes section and gives dn. Okay, so most of the here. Then we talked about probability. You must revise these probability concepts bit once again. They may be asked like calculation, expectation, and all these. Joint PDF. Okay, again correlation was asked. Correlation is very important. They can come in the exam. Then vector of random variables is also important because you will be asked to calculate covariance matrix. You may be given some input signal xn in terms of sign, and then corresponding covariance matrix has to be found. So covariance 0 meaning uncorrelated. So you're talking about inverter or optimal filter, and if xn has to be 0, real mean WSS, and the dn is also similar, then how do you obtain the optimal filter which tries to model this giving the lowest error? So we have to minimize the expectation of e square of n. So we have a quantity which is the correlation between xn and dn, which is the p vector, okay, cross correlation vector, and then you have the autocorrelation matrix of the xn input signal. So we do a lot of math, and finally we obtain that our optimal filter is R inverse of P. This is the best possible filter we can do, but R inverse P cannot be calculated in real life because inversion is impossible, very hard, and we don't have all the signal statistics, and our signal statistics can change with time. So we use the adaptive filter. Adaptive filter uses the gradient descent rule, which is shown over here. The weight changes depending on the gradient of the error. Okay. So that's what I've shown over here. So you get some rule like this, but then we do an approximation in order to simplify our calculation, in order to simplify our implementation, and what we end up getting is this wn plus 1 is wn plus mu xn en. That's the LMS algorithm. So what you end up getting is that you don't exactly converge to the optimal weight, but you converge in mean. That means your answer keeps fluctuating around the optimal vector. Okay, so it's already 9 and the rest, okay, the rest of the weeks are completely theoretical. You have to completely go through the lecture notes where they have, it's all theory. There's not much concept involved, and practice the assignment questions. So I stopped the session for today. Hope everybody enjoyed this series. If you would like to contact me, then please do contact me on this email ID. Okay, then that's it for this session, and I hope you have an excellent festive season and nice exam. Okay then, thank you. I'm ending the call. Goodbye.
Thank you.